Good morning, everyone. My name is Shao Wei Peng. Today is my presentation, and the topic of my presentation is study of an autonomous fruit picking robot system in greenhouse. Study of an autonomous fruit picking robot system in greenhouse. This paper is from the journal Univ. I will follow the outline to introduce this paper in order. The first part is introduction. Greenhouse fruit and vegetables are mostly harvested manually, and the process in Taiwan is labor intensive. But other countries like Japan, Korea, the United States, and some European countries are developing agriculture operation robots to solve the harvesting problem. The objective of this study was develop an autonomous picking robot system for greenhouse-grown tomatoes, which consists of four major. The first one is an effector, machine vision, robot carrier, and a control system. According to the development, the technology of applying robots to agricultural production has become mature, and it needs to be further tested for real tomato picking operation in greenhouse in the future. The second part is methods and materials and methods. In this part, I will divide it into two parts to introduce. That is design of the autonomous picking robot system and the picking test. The autonomous picking robot system proposed by this study consists of four major components: the end effector, the machine vision, robot carrier, and control vision. And the control system the control system consists of robot carrier control, image processing, robot arm and end effector control, and the last one is central control unit. As for picking test, I will present the joint picking test of end effector, and the second one is integration test of the autonomous picking system. Okay, the first part is design of the autonomous picking robot system. The end effector of this study is fixed to the front end of the robot arm. The control signal of the end effector are transmitted from the computer or controlled by the robot arm control unit through the RS-232 adapter card. This picture is the schematic diagram of end effector. The end effector is designed as four fingers. Each finger has three joints, which can bend by spring lift, and each finger is mounted with foam-like soft coating material to reduce the fruit and vegetable injuries get during picking. In addition, the end effector is equipped with the photoelectric proximity switch, two limit switches, and four solenoid actuators to detect whether the tomato is in the cleaving claw and drive the claw fingers to bend. The second one is design of the machine vision system. The machine vision system consists of an image capture adapter card and a CCD camera and a lens. The resolution of the CCD camera is 768 pixels multiplied by 494 pixels. The sensor chip is 1/3 inch and the chip size is 4.8 millimeter multiplied by 3.6 millimeter. And the lens focus is 8 millimeter and the aperture range is 1.3 to 16. The camera transfers the captured image signals to the computer by an image capture adapter card for the further processing, and the images are displayed on the screen. The stereo vision system obtains an actual three-dimensional position of each tomato features for the end effector path planning. The third part is design of the robot carrier. It carries the robot arm, lifting platform, controller, robot arm controller, and PC and carrier driving motor. It has position control in two axes, include X-axis and the robot carrier Y-axis. The fourth part is control system. This picture is the details of the control system. This study used the LabVIEW version 7.1 image control program language of NI as the control software. The control system consists of the robot arm and end effector control, image processing, robot carrier control, and the central control unit. The first one, robot carrier control. Look at the picture on the right. The picture shows the schematic diagram of the control hardware structure of the robot carrier. The computer transfers control instructions to the PLC, which is in charge of the position control in XY directions of the robot carrier. The RS-232 is used as the transmission interface for the computer and the PLC. The four wheels of the robot carrier moves on the rail of the carrier in the X direction, which driven by a 30-to-1 reduction motor of 3-phase, 230 volts and 90 watts. A rotary encoder with 400 pulses per revolution is employed to count the pulses to calculate the moving distance of the carrier wheels, and the platform moves up and down in the Y direction. It's driven by a hydraulic device and a linear encoder with 0.5 millimeters per pulse. It's applied to calculate the displacement of the platform. The second part in image processing. The camera will control through an image capture card using an IMAQ. What is IMAQ? It is a module that was the image processing toolkit of LabVIEW. At first, the camera gets good exposure image and conduct white balance adjustments to obtain a good image. The program utilizes the hue index from the HIS color system to perform tomato grading, then search the tomato position, individual and the external characteristics on two-dimensional coordinates. In addition, the program could also use image processing method to find the center of the tomato if the situation of overlapping tomato is occurred. And the third one is robot arm and end effector. Look at the picture on the right. The robot arm control unit communicates with the computer via RS-232. The picture shows the control action flow of the robot arm system. First, the claw of the robot arm is fixed right in front of the target tomato, and the stretch is in this direction, and drive the solenoid to bend the claw fingers. The robot arm then retracts it in the same direction. The proximity switch detects whether there is a target tomato. If not, the finger will be released by resetting the solenoid, and this action flow will be finished. If there is a target tomato, the claw will be driven and clamped and hold it. Meanwhile, the limit switch signal will be detected to judge whether the limit switch is triggered, meaning whether the finger bends into a set position. If it is not triggered, whether the clamping of the claw has reached the limit will be judged. If not, the clamping will continue. If it has reached the limit, the claw will rotate it to remove the tomato from stem. The robot arm will then be driven to place and remove the tomato into the basket. And the fourth part is central control. The picture on the left is it shows the contraction flow of the picking robot system. It has 3 stages. And this is picking test. The first one is joint picking test of the end effector and the vision system. The working distance of the camera is 660 millimeters, and the feature field is 396 millimeters by 297 millimeters. And it is accounting for 52.57% of the visual field area. If the barycentric coordinate of the target in image analysis are in this range, the target can be picked by the end effector. The third is the formula of the picking success rate. The second part, integration test of the autonomous picking system. This picture is content carrier movement, platform up and down, image acquisition and analysis and picking. The third part is result and discussion. The first one is prototype of the autonomous picking robot system. This picture shows the picking system. The dimension of the greenhouse grown tomato picking robot system are 1050 multiplied 700 and multiplied 1350 millimeters. And the total weight is around 2,190 newtons. This table shows the result of the integrated picking test. As seen, the overall picking success rate is more than 89.63%. The average picking success rate of the test bowl with diameter of 60 millimeters, 70 millimeters, and 80 millimeters. That were 94.83% and 91.83% and 89.63% respectively. The average time for picking a bowl was 35.96 seconds. In other words, the picking operation capacity per hour is 100.1 bowls. The final one is conclusion. This study developed a greenhouse-grown tomato autonomous picking robot system. The picking robot system consists of a robot arm and an end effector, machine vision, and a robot carrier. And the control system consists of 4 units, including a robot arm and an effector control, image acquisition and analysis, robot carrier control, and central control units. Let's use the LabVIEW version 7.1 graphic program language were used for the constructing the control program. And the second, if the field range is 396 multiplied by 297 millimeters, this range within which the end effector can pick target is 336 multiplied by 184 millimeters, accounting for 52.57% of the visual field area. According to the picking success rate of the end effector integrated with machine, since the end effector size is fixed, a higher accuracy is required for picking large fruits. Therefore, fruit size influences the picking successful rate. This study developed the software and hardware for the greenhouse-grown tomato picking robot system, and the expected function requirement was met. The practical greenhouse-grown tomato picking operation test will be enhanced in the future, so the system will be more practical and applicable. I have already finished my presentation. Thanks for your listening.
Thank you. Yes, please.
Thank you for your presentation. I have learned about can the robot do the same work from the outside, or it can only do for the greenhouse. If we can do it, what's the difference between the two places?
In this study, the robot can mention the operation in outside, but I think in the future it can do it. You mean the difference in indoors or outside? In my opinion, I think I will look for other information now to answer you after that. Okay.
Okay.
Because the article, the study it didn't mention it.
Okay, thank you.
Thank you for your presentation. I have a question. How is your robot to pick up the tomato? You cut or you twist or how do you pick up easily?
The PowerPoint I will mention is use the end effector to throw it to pick up the tomato. They use the robot arm over there. This one is the end effector. We can use it to pick up the tomato. To pick up it. Yeah.
Okay, thank you.
Any questions or comments from Japan?
Are there any questions?
Hello, and my question is about picking robot with four fingers. You say that fingers are coated by something soft material to reduce the damage. I would like to know what kind of material. Is it sponge, gum, cotton, or something else?
Please repeat again your question.
Picking robots of four fingers for arm. You said the arm is covered by something soft material.
You mean use how to avoid the tomato is get hurt? You mean it?
To reduce the damage of tomato.
I will show the PowerPoint to answer your question. there are in end of vector there are 4 fingers and it has a material of soft. Wait for a minute. Each finger is mounted with a foam-like soft coating materials, and this material is it can reduce the fruit and the favorable get hurt by picking up. Can I answer your question?
Okay, thank you.
Are there any more questions?
Thank you. I'd like to know what is the maximum load picking carry capacity of a detector. I mean, the individual capacity to pick up in terms of weight, easy times, and pick up. The individual capacity, how much it can pick up at times, that means load in kg, kilogram, like that.
Oh, the end effector is weight. It can. The study is not mentioned, but it can mention the when. I guess it can because in my conclusion I mentioned the large fruits can use this system like watermelon or the large one. So I think the weight limit like a tomato one and
100 gram, like 100 gram.
the same is around.
Okay. Next one is, I'd like to know, would you can explain the path planning system of this robot? Path planning, based on which features or character or parameter? The path planning.
In this picture, hello.
Yes. How it is work for path planning actually?
You mean how to move it?
Go forward or backward. Go. How it is go forward.
Over. If the system will continue will operation initial from A like the pen through the vertical or horizontally to move, and the pen on the picture is the machine system to move on.
This is only from the picture, it's like railway. Maybe. Okay, thank you.
Thank you.
I have some comments. The system equipped with the stereo vision system. So not only the XY coordinates, but also the depth, three-dimensional location. So, okay. Any comments from Japan? Questions?
Any more questions? So, no more questions from Japan.
Okay. So thank you very much for